Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Well, my name is Erik Juhl. I'm a professor of computer science and currently director of the eScience Studies program at the University of Copenhagen. And I'm very happy to welcome you here to this session on eScience inspired education. I'm co-chair here. Jan Tzu is the other co-chair for Microsoft. She's busy running around arranging stuff, but she'll show up in a few minutes, I'm sure. And we're not that many that we cannot structure this as a session where you are welcome to ask questions and interrupt. We have a little bit less than 2 hours to go. We don't need to use all the time. We have nothing to say, and I would certainly encourage you to ask questions and give opinions. And I'm giving a short presentation in a moment, and as I usually say, you are quite welcome to interrupt during the presentation. You are probably much nicer and kinder than the tomato-throwing students I have at times. So, apples! You're supposed to give that to the teacher. And here's Jan Tzu, who's co-chair. Okay? And with that, I'll get started on my talk. I should say we're structuring this. We have a few short talks just to get things going, and then we'll have a discussion afterwards. And I have a few questions I'll be posing you if the discussion doesn't get going all that fast. So let's move on. This is a quote I like using because it's not mine, and that is that the next 10 to 20 years we'll see computational science firmly embedded in the fabric of all science. And this is a really major change, not so much for computer scientists as it is for people in other areas of science. Many are already doing eScience without knowing it. When we started investigating this program, we went out and talked to lots of people in lots of different departments and discovered that they were all really doing eScience. The geologist was, the first thing he did was jump up and start showing a visualization he had on a wall and explaining things from using that. But lots of them have a very either poor or none or some kind of ad hoc education to actually use computer science and computational science within their fields. And there's lots of reinventing the wheel. And this problem used to be solved just by adding a programming course or something like that to biology, physics, chemistry, whatever ology it is. And that doesn't work any longer. One solution would then be, I'm a computer science professor. I can go tell all those other guys how to do stuff and how to do databases and how to do visualization in all those other departments. Well, that's a very, very hard way of doing it because there's an enormous amount of resistance. Not invented here is very strong. Whoa! Oh my goodness. This thing changed very quickly. So our solution is to establish a separate eScience graduate program. We started in August, and it's a separate program that's cross-disciplinary, and in some sense it is a study program just like physics and chemistry and computer science. So when you're choosing what you want to study at the graduate level at the University of Copenhagen, then you pick from the list of physics, computer science, eScience. And I'll get into why it's a good idea for that to be separate later. I'll just describe the program briefly. Entry requirements is that you have a bachelor in your own field. That means any of the natural sciences, any physics, chemistry, biology, whatever. We obviously just want the best. That's what everyone says. And a very short description of the program is that it's 1/3 computational science and 2/3 eScience courses in their own field, in people's own field. It's a 2-year program on top of a bachelor's, 120 ECTS, if that says something to you. That's a European standard for credits that's trying to be introduced all over Europe. There are 4 compulsory courses, and then after you've taken these, or in concurrent with them, you take a number of other courses that are on our list of eScience courses. These are courses in each of the different departments that has eScience component in them. So the idea is that you actually build your eScience education by taking these 4 core courses that gives you the basic tools, and then you continue working with these tools in your own field, in courses in your own field. And the best way of learning this is also by doing individual projects. So we have a strong emphasis on learning by doing. And we have the standard thesis is a half-year full-time work, but experimental theses can be up to 1 year. eScience components, well, this is all familiar to. It's modeling and simulation. It's data acquisition and handling. It's visualization. It's high-performance computing and grid. And so the 4 compulsory courses cover these areas: a scientific computing course, a stats course, a data mining, and a scientific visualization course. So the 4 required courses. And I'll just briefly describe them. The scientific is learning a lot of standard methods. It's very experimentally oriented, learning by solving lots of smaller problems and working with different programming languages. And it's an interesting course in that it's actually taught by members of 4 different departments. The guy who is running it is a computer scientist, but he has lots of relationships to other and assembled this. And I'll get back to that point a little bit later. A statistics course. Now it goes off again there. Darn, sorry. A data mining and database course, which is you need to be able to handle data and store it and find stuff in it. And then a visualization course, which is something where we're also trying to get people from different departments to come in and help on this course, with less success than the scientific computing one. And the visualization is both actually visualizing stuff, drawing stuff, but also more data mining and ways of doing that, pattern recognition and so on. And as I said, these other courses you choose amongst a long list that we've compiled from courses where you can learn eScience applications in other departments. It's very project-oriented in that we like that lots of the work that you do is that you take up some kind of problem, a real problem, and then you start solving it. And what I haven't noted here is that it's actually also common for our students in Denmark to work together in groups. And working together with someone else is a much better way of learning. You're ping-ponging back and forth all the time. And another difference from at least my experience with the US educational system is that there's a strong emphasis on delivering documentation of what you've done, both the analysis of a problem, both a description of the problem. What's a solution worth if you haven't stated what the problem is? And writing up a report on the results and evaluating them and putting them into context. And then you do a thesis. Some more thoughts on this is that I think one of the reasons we've been able to establish this program and actually have goodwill at the other departments is that it's not established in a particular department. It has no department. There's been an eScience Center established, which in some sense you could call a department, but it's not an independent department. It's just a center where we do research and is where we apply for grants and get eScience level. And as director of eScience, I refer directly to the dean, not to a department. So when I'm director of eScience, I am not a computer scientist. I am a director of eScience. And this actually makes a big difference when I talk to people because it means we get good support from a few forward-looking people who know that eScience is the future in their particular field. And then I get good contacts with these forerunners, as I call them. And we're not trying to push our way of thinking into someone else's department. We'd rather have them come to us. A problem, whoa, darn, this thing is student mobility. It turns out that it was actually easier to get support among these prime contacts in different departments than it is to get students in these different departments to actually sign up for this. And I can see that it takes time, calendar time, for people to get used to new ideas, that if you have a bachelor's degree in chemistry and then to decide, well, I don't want to do a master's in chemistry, I'd rather do it in eScience. It takes time for that to establish itself. So we only have 8 students, but there's a slow trickle. Every month there's a new student who comes around and says, I'd like to hear a little bit more about that, and how do you actually enter? And then actually we already have 3 students from outside of Denmark that have found the program on the internet, just surfing around. One from Norway, one from a Saudi Arabian who did his degree in Lebanon, and Hong Kong Chinese. The short-term vision is to slowly build success by working with these students. Note that it's not expensive establishing the program because of the core courses, most of them are variants of courses that we already have or will attract lots of students regardless. I mean, even the visualization course, which is a new and specially designed for eScience course, has lots of people who want to take it from other fields. And then get non-conservative, as I call them, and interested faculty to actually introduce eScience thinking and courses slowly but surely in their own departments. And we're doing this within the College of Natural Sciences, but if we get successful, we'll sort of reach out into the other colleges at the university. The long-term vision is that 20 years from now, there will not be an eScience program because it will all be an integral part of all science. I think George said that in his talk earlier today.
I said 5 or 10 years.
You said 5 or 10 years, yes. Okay, so you're an optimist.
Just like there's no program of statistics?
No, because no, the point.
Statistics does not fade away, even though pretty much every department uses it.
Right, but there will be a computer science program, is my point. And essentially, you can think, if you look at eScience as applied computer science, as like putting math into all sorts of fields, then that's the vision, basically.
There are departments that feature their own statistics courses. There are other departments that don't.
Right.
They back them out to staff.
Right.
Yeah.
Thank you. Any questions? Yes? Whoa.
One of the, you were saying that you were having difficulty with students. One of the interesting difficulties that you face PhD students that were PhDs in eScience, even though they were subjects attached in the hydrogen physics, astrophysics, or something similar, is that unfortunately there's no career path for those people.
There's no what?
Career path. Because they come out with a PhD that no one recognises when they try to go to their first postdoc.
Okay.
So whereas if you had a say for example, computational biology, everyone knows what that is.
Right.
Computational
Ah.
climate or things like that.
That's interesting because some subtle differences in the structure of university programs can make a big difference. At the University of Copenhagen, you get your PhD at the College of Natural Sciences, is the one that grants you the PhD. So technically, there isn't a computer science PhD. You can look at the title of the thesis, and then I can describe what I did, and then I can convince you I'm a computer scientist. Right.
That's what we talk about, identity issues. So when
But-
they get themselves monitored,
But one more point I'd add to that is that I visited, a couple of years ago, when I was starting to do all this, visited the American Museum of Natural History in New York, where they do lots of research. It's a big research institute. And I met someone there who was a zoologist and who wanted to become an assistant professor in zoology. But he was doing his PhD in computer science because he knew that once he got out there, there's a gazillion who have good zoology, but he had a computer science PhD that he had bent over towards zoology, and that he felt that he would have much greater chances of getting a job that way. Yes?
So just a quick follow-up there. One of the things though is that where you have a PhD in eScience, what you find is that you go up for your first postdoc, and you'll find people that have a PhD, an official astrophysics PhD, for example, and they will have done lots of computational science in their astrophysics because you can't not.
Right.
So what you'll find is automatically the panelists where you interview will say, well, we've got an astrophysicist against
who's already
scientist
Right.
thing, and boom, there you go. And so it's very difficult unless you, I think, fronting with a particular domain area will always end up with a more employable person.
Right.
Not
Right, and that's what I'm saying is in our program that we have designed it so that you can get yourself a degree where most of the time you've spent taking courses and doing work in your very own field. Okay?
I have a comment and a question, and Mark relates to this now. We have a bachelor's degree in computational physics, 4 years, almost word for word identical to what you have here. Same number of introduced courses, same emphasis on writing, and much the same courses. And it works very well. The comment to answer there is we find students with a bachelor's degree in computational physics can get into graduate school in many programs immediately, in the U.S. maybe, and they can get research associateships, and they're hired to work even the first summer because they have computing skills which the other grad students in physics don't have.
Right.
So they're hiring as domain experts with computation training?
Yeah,
Or
well, they're
vice
hired
versa?
to go into someone's research lab or start on a research project even before they've had their graduate classes because they can compute,
Right.
and that's what physics is a week in. So it gives them an edge.
It gives them that. That's just like my zoologist example.
And the real question I have to you is, it seems kind of obvious, but this would be excellent for students to do and get a PhD someplace else as well.
Yes.
Does that happen?
Yes.
Are these joint students in some cases?
Well, we don't have very many right now, but
Eight's a good number.
it's a good number, yes. And the way that the Danish system is set up is that you can't become a PhD student before you have your master's done. You have to have a master's first. So it's the model of bachelor, master's, and then PhD student, and not as in the U.S. where you can start a PhD program immediately after your bachelor's.
So that seems to lead in fact, if someone goes into, say, chemistry, after they have this, maybe they get a PhD in computational chemistry.
Right, or in chemistry, for that matter.
Chemistry, but then you can call it.
Right, right. Yes. And
So there's two ways there's two target audiences for degrees in eScience. There's trying to train the people who are going to develop the next generation of eScience tools, which might best be done in the computer science department. And there's trying to train scientists to think computationally and use these tools, which is what more this.
that's more what we're focusing on, yes, sir.
We've been trying to push in this direction at ASU. I've been thinking about this a bit. And it seems to me, we've been talking about how majors and concentrations. I don't think that's the best way to get this out there. I think that an eScience minor is really the best way to go. So whether it's at the undergraduate level or the graduate level, that they've got their main area and they're taking some courses
Right.
as a minor that
And,
helps them.
and again, essentially that's what we're doing, as I said, because it's 2/3 their own field and 1/3 these core things they have to take. But for technical reasons, we can't call it that.
We don't call it that, but at least at U.S. universities, we probably would be called an eScience minor.
Right.
Okay, great.
So that's what we'd like to do, but we can't. Yes. And George, you had a question too?
Do you have a website for your class?
Excuse me?
Do you have a website for a program?
Yes. I'll make sure to send it out to people. So. And you had a question. One more question.
So you report directly to the dean, so doesn't that make you a department?
In some sense, yes, but a department consisting of one employee, one part-time employee.
So I'm the technical manager of the e-research centre, so we are a full department within the university. But we had to do that because we sit inside mathematics, engineering and physical sciences purely for an internal administrative reason. Keep that going.
Okay. Anybody know what this?
Being a full department does have certain things that give you
That's
certain
better.
weights in the university
Right.
rather than a
Okay.
research centre which has less gravitas within other departments.
But for political reasons, I think it's highly unlikely we will be able to have an e-science department.
Could you have a computer science department?
Excuse me?
Could you have a computational science or applied computer science?
Right, but it would then, I think one of the reasons that we have an easier time getting people to cooperate with us in terms of teaching and courses is, again, this thing I pointed out, that the ownership of this is everyone, the chemist and the physicist own this e-science education just as much as the computer science and the math and the stats people do. Okay?
So
no, let's create this program on the side that everybody can agree on because it's not mine, but it is mine. But the students will gravitate to take it, and so it's sort of a shortcut of getting to where we really want the curriculum to be in chemistry and biology and earth science, where you want them to take a couple of courses, that's more modeling. That's my hypothesis.
That's.
We did this at Rice. We had a computational science and engineering degree, and it was really set up as there was no department, primarily taken by earth science students and some other physics students, and they came over and took it. But now we don't need it because they slowly kind of, they either accepted that they have to offer a course.
So.
Well, I think it's more parallel programming HPC courses, not the.
Right. Okay. So it was very well put. That was basically also our idea, that the students are smarter than the faculty. But I'm not going to say this any closer than 5,000 miles from Copenhagen.
I think one of the problems if you put a program together with existing courses only, and not like you've done, just add these sort of bridge courses, these glue courses, is you don't necessarily get the viewpoint of a computational science.
Well, no, I do think we need to create new courses. Yeah. But we should work together, and we shouldn't necessarily have to stand up as sort of a minor or something. Like that's my hypothesis. I think it is.
All politics is local.
Right. Okay. Well, thank you very much for the questions. And and now I'll introduce the next speaker, which is Rosalind Reed.
Great. Yes. Thank you, Eric. Yes. Hi. I'm neither a computer science nor a natural scientist, so I'm, sort of in the middle, a bridge person. So I wanted to just give you a little bit of the flavor of an experience that I've had at Harvard that I think it's a response in part to the workshop, the Microsoft workshop we had on computational education for scientists, and sort of a story of what happened at Harvard after I came home from the workshop. So I was a fellow for a year at the Initiative in Innovative Computing at Harvard, which I need to point out is not part of the computer science department. It's an interfaculty initiative, and it's intentionally all about applied computer science and computational science. So we thought that the IIC could be the bridge, could be an outside organization, have the same kind of role that Eric had being outside the departments. So I was asked as a fellow before I became executive director to look at what we could do about undergraduate education, which is really the big focus at Harvard right now. And I decided that after interviewing a lot of faculty and getting a lot of the pushback between departments continually, that I would try to see if asking the question of computational thinking could raise the dialogue a notch. Just try to, is there a plane on which we can all talk? So I did a little survey about to the natural science faculty before talking to the computer science faculty. And this is sort of the premise. Everyone agreed that computation is going to be the core of science soon, and that undergraduates now are going to be doing it. They're going to have to be computational, and that we're not integrating it into the curriculum now. So this joke at the end is just because one of the first things I learned at Harvard is that the Faculty of Arts and Sciences is a bunch of gods, and you just have to go and ask Mount Olympus what to think. I love faculty, but it's kind of interesting. So I did an online survey, and the most interesting thing about my survey results is the narratives. So there is some data, but it's not very scientific. So I just wanted to talk a little bit about the narrative responses. And I'm going to skip very quickly through them because of the time, but I have some handouts and I can make more. I didn't know how many people would be here. And then I have the slides. So you'll see a whole lot of narrative responses that I'll kind of flip through and just highlight a couple of things. So I started with Jeanette Wing's kind of definition of what is computational thinking, and thought maybe we can get some curriculum change going around this concept. Picked a couple of her examples out. If you've heard any of her talks, you know sort of some of these ideas. I was working at the time with Lynn Stein, who some of you might know, who's kind of been an educator in computer science who has advocated a lot of interesting project approaches, and she gave me some additional conceptualizations. So I have since now gone and had a conversation with the computer science faculty, and we have a real dialogue going. So these are the kinds of questions we asked, and here's one. This is Lynn's suggestion. When she starts conversations with scientists, she asks, how has computation changed what you do? And then, so these are sort of some of the sample responses. And it was very interesting. Starting the conversation this way really made people think about their own particular field. And the answers were very different from one field to the next, which, is one of the things you can say eScience, but we all know it's many kinds of science. It's not one thing at all. So, we have people talking about modeling. We have people talking about large data sets. We have other people talking about algorithms. We have the best person who was most holistic was the person in nanotechnology who had data acquisition, analysis, graphics, simulation, that sort of thing. So again, I'm glad. I actually have big spreadsheets of all this if you want to look at it anytime. So then I asked question 2, which was the types of computational thinking you expect to become important in the coming decade. So a lot of this was the same as the first one, but I wanted to highlight this climate person's comment. How to reduce and abstract a real-world problem into a computationally solvable problem, and how to map the results back to the real-world problem. This is very classic computational thinking. And it was very interesting that I found certain faculty who are very eager to talk about how we can think about these things that way. And later on, I harvested their, yes, I volunteered to do faculty workshops on this, and so we're going somewhere with this. Anyway, these are some more of the answers. This cosmologist was looking at sort of large databases, scripting. A lot of this was skills, but again and again, this question, how do we deal with large databases, did come up. You all know this, so this is nothing that's new. Again, I'm going to quickly go through some of these. General programming skills, but some people are willing to think not just they need MATLAB, to think wider and think people need to know how to think about programming rather than just know a particular high-level program. So then, with question number 3, I was trying to get down into skills and abilities. And some interesting things that I came across also were this fellow in nanostructures, pattern recognition in the most general sense. Again, it's a type of language. Can we talk about pattern recognition, and can we talk about that as a kind of computational thinking? So these are just some more snippets of questions. The other thing that came up is frustration of many faculty. Why we can't think about computational thinking because we can't get the basic math and science knowledge up and the interest, and students really don't want to be doing a lot of this stuff. Then another interesting issue, and that is worry that teaching computational thinking or focusing on computation gets students away from the fundamentals that they need to know. Do they understand the observations and the problems with the instruments and the nature of the stuff that's out there that these data represent, or don't they? Do they just see it as data? It's just as bad to, step away and think computationally when you don't understand what nature. You can't ask a good question of nature unless you really are understanding the first principles and the systems that you're dealing with. So some conclusions. Large data sets was a big focus of the responses to the survey. Disparate sources of data and how to put things together. This fear that sophisticated tools are actually blinding students to sort of some of the underlying science. Some of the programs are just too good, and that has affected how faculty think of these things. So, okay, I don't really mean they're too good. I mean that it's like the student is several layers away from the actual observation because there's pretty pictures happening or something too deft. These levels of math and science and quantitative understanding and so forth. So again, just quickly flipping through, what we're doing right now is experimenting, first of all, with building some more research experiences, because until we have some curriculum work done, which I'm not sure what form it will be in out of these conversations. The ISC is an organization that provides a lot of research experiences, and we've had fantastic kind of results from the research experiences. So we're going out and trying to get a lot of grants, trying to pull faculty in, do some grant swarming at the ISC to pull faculty from many departments and say, can we bring cores of students together that have projects together and they learn computational science that way by being embedded in a project that is heavily computational in their field. We've had a lot of success with this, one NSF grant and another looking like it's coming down the pike, with a lot of REUs and so forth. So then we're going to have a winter session. We're going to play with some short courses. We're building some labs where the computer will sit there, and there's a lot of discussion about what that computer is going to do in the wet lab and how you're going to teach students to model beside their, to do their wet lab experiments and then model and talk back and forth, and how can they understand that in biology. So we're starting some faculty committees, and we are working on what to do with the Intro to CS course, because science students have just not been taking CS 50 and 51. The business students are taking it, the social science students are taking it, and the science students are not. They're smart. They're beyond it. Yeah. Right. So we were trying to talk about whether we can have a course, a track that focuses on scientific problems in that Intro CS class. But right now we're trying to experiment with a couple of science projects that we throw at the students to see if we can also interest more of them in science. I don't know. And then just very quickly, this is the path that I mapped out for the IIC on education. It involves a whole lot of stuff. I mean, the point of this is that we are working on what we're doing at the high school level and starting some graduate curriculum development, hoping to transform the master's in computer science that we have now into something with some scientific applications, and doing a lot of other things because we feel that they all feed into things, and we'd like to bring some high school students that are very sophisticated into the picture too. So I want to say, first of all, I've learned from talking with people that computational science, of course, has to not be thought of as some sort of substitute for all the basics that people think we're trying to get away from. And so fundamental undergraduate education has to happen first. And then, on the other hand, there's a lot that these faculty I've been talking with now believe can be done by bringing more computational science into the undergraduate curriculum wherever we can seed it. And this last one, which is classic Lindstein thinking, is teach people to actually cleave their systems into computable parts, abstract, represent, model, map results back. We're going to actually try modules in the interdisciplinary first-year courses in which the students have to do that. We have life sciences, an integrated freshman curriculum, and then we have a physical sciences integrated curriculum, and we'll try putting the computational model in there and see what happens. So I am happy to chat about all this, and I wanted to let you know just where we were. So that's good. Okay. Great. Yeah. Good. Okay. You talk too.
You wouldn't think of doing something at Harvard without speaking to the faculty.
Yeah.
Have you spoken to the students?
Oh, yeah. Yeah.
I found when I teach these bridge courses, the only courses I've ever had where they thank me at the end.
Yeah.
Because they learn the skill, they can get jobs, they can
Right.
do research.
Yeah.
That
Right.
would be a real balance here that may change some of the faculty.
Yeah. Well, I've been fortunate that I have a group of students who actually sit in the same office with me, and so we start with the students who are the summer interns and our other kids. But the important thing is that you can have conversations with undergraduates They don't yet know these problems that you've just been talking about that they shut down with, oh no, I have to follow this very direct career path that it's exactly my advisor's path, and that's how I'm going to get the academic job. But the undergraduates are kind of open, so I've had wonderful discussions with them.
Maybe the exit interviews with the students when they realize what they're missing, what
Yeah.
they have to learn,
Yeah.
what they didn't master well enough.
Right. Yeah. That sounds good. We're not that far yet. Yeah. Great.
So a lot of responses to your survey class in some ways as grand challenge projects or
Yeah.
science or subjects. I'm very interested in what the small and medium researchers came back, the guys that are one person working on their own in research. And the other one I saw very little experimental science.
Yeah. Right. Yeah, I should mention just these terrible qualifications about my survey. It was entirely voluntary. Some departments distributed it to their faculty. Other departments, very lackluster response. But I had to rely on volunteers. So those are the motivated people who. It's a self-selected group. So I'm afraid. Yeah, you're right.
So I think primary data is very important. Talking with the faculty department, as there is so much knowledge, which is a good idea.
Yes.
That's it. So we all agree that eScience is something that's going to sort of percolate into the fabric of science in a number of years, but that's 5 to 10 or 15 or 20 another question. How is it going to affect the process of doing science?
Good question.
Any sense from the answers of what people are speculating? I mean, a little bit this wet lab integrating with computation.
Right.
Always in that direction.
Yeah.
Do you have a clearer sense than that?
Well, because I asked specifically about computational thinking, I think that directed the responses to this a little bit. So that one person who talked about abstracting a problem and modeling it and mapping it back to the real system was was understanding what I was asking. So those answers, there were several people who had process-type statements that they made. Yes, but thinking, right, and that's the magic of it, because a few people actually recognize that as computational thinking, but yeah, 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 yes,
Since computational thinking is so broad, it's probably appropriate
yeah,
to do it as opposed to somebody else. Computation shows up also now in social networks. And opens up communications and channels of interaction which in my generation were unheard of.
right.
How is that migrating into the picture?
That's a good question. No one in my survey actually answered that. The closest thing was a biologist working in genomics who said, we've got to figure out what all this semantic stuff is, because somehow it's going to change how we work with each other as well as our data. That's as close as they got. We are working at the ISC on collaboration frameworks for science that are entirely online, and they're very semantics-based. Where you collaborate partly around the collective data mining in your field. Works very well with ontologies in biology, is more challenging to apply to other fields. That's more of a research project about collaboration, but it's very important, yeah.
And I agree with you, that's an underrepresented thing here.
Very.
It's just as important as some of the more traditional eScience.
Yeah.
So one of the things that is not, I think we're not talking about explicitly, I think it's really important, is whether or not we want to be teaching science, training next generation scientists to do things, fairly low level things like how to program in C or Java or whatever, or whether we should be training them to think computationally, but to use higher level tools that say computer scientists are building.
Right.
And I think this is a real issue. My opinion is that in most cases, we want to move toward training in higher level tools, and that we should leave the low level stuff to the people who really would agree. But at least we have that discussion.
Yeah, can I suggest a synthesis? I think scientists should know enough about the computational process to understand, to guide the development of better tools for science.
Yeah, sure.
Yeah,
For example,
but
they need to know
they don't need to.
numerical analysis algorithms, or they simply need to know how to
good question.
So I think actually going to there, I think you should be able to describe the algorithm. Being honest, you can always find someone to program it for you. You can always pay someone to program it.
Yeah.
But the person that you ask to program it will not have the understanding, which is the bit that we need to be able to.
They need to understand what it means to simulate a different equation model. They need to know how to do a round-up error.
Probably.
I don't think so. Okay, yeah, but at least we need to know what
They need to know round-up error exists,
Oh,
and
yeah.
what it looks like when it comes up.
Oh, yes. Yeah.
At that.
The danger with going purely to the high-level language, though, at the same time, is that people start to think, well, that's obviously the way you do it, and what you find is you spend hundreds of millions of pounds building very, very expensive computers to run completely inefficient.
Yeah. Oh, well, no, but we certainly should be building those systems as well. But I'm not sure it's the people with training in sciences who should be doing that, because they're likely to not know. Let's get people who know how to make them efficient.
If they can prototype it, then they can pass it to someone else.
I had a real answer to the other question. I think if you're going to use a petascale system as a scientist, you need to know some of what's inside a black box, or you'll never make it work well enough to be reasonable. The real comment I wanted to make is, there was a good question
Why
about...
don't you give them the mic?
Oh, yeah.
The real question was about whether computation would change the kind of problems we teach and stuff. And I think the answer, I'll use physics as a good example. Physics has taught the solutions for the same simple problems over and over again in more and more detail, because that's all they can solve. And they've developed a lot of mathematical, solve analytically. And they've, books like Jackson, which is a classic, has all these analytic techniques which are really obsolete and are only good for a very limited number of problems, and they're not at all good for computation. So I think it's hard to get the physicists to change just on those points, but that will be different. We heard George said in his talk, there's more complex problems out there. That's what ones will be solving, and they're more realistic. And the simple problems, we shouldn't be focused on as much.
Yeah.
So to come back to that directly, as a physicist, I would ask, actually, what are we trying to do when we're educating people? We're trying to provide the next generation of people that are not just going to be researchers, that are going to be the people out in industry and places like that. And so from that point of view, I do find it very interesting, outside of the vocational courses, that physics is, of course, the most employed by anywhere in the world. But there, we need to make sure that we're able to feed back into the courses the real-world problems, more than just what we think are the real-world problems as researchers. And that's a very, very hard thing to do if you're going to have a consistent course and a consistently measurable course as well.
So can I answer him? So I have it on my slides, but they're not up there. If the AIP has done a study of what's important for physics graduates 5 years after they graduate, and the least important thing is their knowledge of physics. The most important thing is their ability to solve problems.
Ability to think.
Yeah, to think and to analyze. But physics knowledge per se is the least important. And that's both true for people who go into the computer industry and for people who stay in science and engineering. And I haven't...
Yeah, and I can add to that at the University of Copenhagen they've done some surveys over where people go to, and that only about 30% of the mathematicians are working as mathematicians after 5 years. They're working all sorts of areas, and it's the methods they've learned, the way. It's good education. They learn to solve problems, learn to think logically, and so on. Okay, any more questions here?
Okay.
Or should we move on?
Okay, and
thank you very much.
Be glad to... Yes, Jan is collecting email addresses. I'll be glad to just email everybody. Right. Great. Okay, do you want the whole spreadsheet if you want it up there, or just... Okay,
If you're comfortable, we can put it on the website of Computation Education.
Sure, yeah.
Talk about that, please. Okay. Rosalind, you want to... Okay, and the next speaker here is Majid, and I'm not going to try to pronounce your surname. I'll leave that to yourself. Okay?
Would you mind taking this off so it doesn't bang on it? Do what? Take this off. This. Thanks. Perfect. And you can switch that on.
Oh, it is off now? How do I?
Takes a second. It's good.
I'm an engineer.
Engineer. And you, sir?
Okay, so I guess first thing, how to pronounce my last name, Sarafzadeh. 2 parts. I'm going to talk to you about wireless health, perhaps a new area in science and engineering. I'll tell you about our experiences at UCLA in this area, what kind of reaction we have received from students, from industry, from the community, etc. How much time do I have roughly?
Oh, we're open until like 5:30. So this is like, feel free to ask questions, and we have one more speaker. Yeah.
Okay.
Yeah, after you.
Just stop me whenever. We have started a sequence of courses, and Jan was there helping us, supporting us from pretty much day one. And I'll share some of that experiences with you. Some of the problems that we are trying to solve are of this type. There has been, these are ulcer, people with diabetes. They form this ulcer. It normally results eventually in amputation of the toe and the leg. These are real problems, and these are not long-term problems in the sense that you could get these ulcers very easily. Just try maybe now, if you have a hard surface, chair or something, push your finger on them, just one finger, really hard, for 20 seconds. Look at your finger, what do you see? White color. Reason is the blood is not flowing to that area. Do that for an hour, it's going to hurt really bad. Do that for a day, you're going to get close to this. So it's not a 10-year problem that's going to accumulate. And people with diabetes, because they don't have sensation, normally they do not realize that they are getting these ulcers. So it will quickly result in amputation. Last year in 2007, there were 90,000 amputations in US. Each costed between $50K and $125K. So you just do the math, and typically insurance is paying for this, a lot of money. So wireless health is an area that is getting a lot of attention across the country, mostly at UCLA because we are kind of advanced in this area. We think computer science is changing. Multidisciplinary issues are coming into play. That's what our students are saying. Students' interests are changing. We have a hard time getting a student to focus on compilers and only compilers and not seeing the relation to what is out there. There is internet. You know, when I was a student 30 years back, we were just doing what we were told to do. I was personally doing theoretical computer science. These days, it's a hard time having students do that. And the business world is changing. Moore's law is stopping and all that. In 2006, the budget for healthcare was $2.6 trillion. That's a lot of money. So if businesses get into that area, and a lot of them are, and I'll tell you who in particular, there is a lot of money to be made. And students are very excited about this because they are seeing these impacts. So the 3 courses that we have formed initially at UCLA about 3 years ago was an introductory digital design lab. But from day one, we trained them on various medical issues and medical problems. There is one 52B course, which is a capstone design course. The first half of the course, again, a student learn about advanced digital system, wireless, and all that. And the second half, the students come up with a proposal, just like a business plan. And they say, I want to build this. I'll give you some example of the stuff they have built. And we will criticize them. We say it's a bad idea. The market is not there. The engineering challenge is not there. You can't sell it, whatever. We give them feedback. And in the second half of the course, they actually build a very decent prototype. The course one, and Jan, for example, has been as a judge in our proposal presentation. We criticize the student. We are tough on them. We encourage them depending on where they go. 151C is purely project-based. Day one, we bring a few doctors. They give lectures on what are important issues in the health industry. The student come up with a business proposal, they build it, it's an entire course. The last day of the class, the student come up and present their prototype and their ideas and everything. And I have a panel of maybe 5 venture capitalists, a few business professors, people like Jan or Jan from industry. We have engineering professors, medical doctors, a panel of about 15 people. They come and listen to this presentation, and they grade the students. Students just love this. So that's one aspect of it. I got into this area about 5 years ago. It was very hard work, communicating with these doctors, understanding their language. We had meetings with different doctors every day. 90% of the meetings were totally useless. We just didn't get each other. We didn't speak the same language. After 5 years, we are at a stage that UCLA as an institute have approved this institute, Wireless Health Institute. They have funded us, even though the economic situation is not great. They put their money. 7 deans at UCLA put their own money for us to get this thing started. So that's all good news. And students are they just love this stuff. Because at the end of the day, they have a product and they can see the use of it. We have this example that we say when the student goes and explains this project to their grandma, they all get it. And I'll give you some examples of that. So emphasis of these courses on interdisciplinary research. Because of my personal interest, most of these projects are in healthcare, but not necessarily all of them. There are some in, for example, you saw some on piano playing, pool playing and all that, but a lot of them on medical. And there is a very quick transfer of ideas to the external world. Some of these projects have already resulted in startup companies in a very short amount of time. Some of them are being done at a very large scale in Los Angeles area, being deployed. I'll mention those also. These are details of the timeline of what we do in various projects. It's probably boring for you, but if not, email me and I'll be happy to share all these details with you. How do the students get started? It's a very challenging course, all 3 of them. The first complaint they have is that they are spending all their time on these courses. The first praise they have is that they love every minute of it. So after the course, we get really good evaluation. During the course, we get a lot of complaints. That's the way they are. Okay. The kind of technologies we provide with them is a wide range of things. We give them video cameras with chips on them, many FPGA type of system, many mobile devices that runs, for example, Microsoft Windows. We give them robots of various type, like iRobots, etc. So we give them a lot of platforms and we say, do and pick whatever you want and do whatever you want with them. We give them iPhones, we give them G1 phones from Google, being open platforms and all that. So one example of the things they have done is, let me go back, are these assistive devices. So starting from cane, going to crutches, walkers, and things of that type. For example, there are 4 million cane users in US. Have any of you ever used a cane because you went skiing and broke? How many had to use a cane in their life? So I don't know if you remember, when they give you a cane, they give you a set of instructions. The instruction says, and I read this specifically in our VA hospital, it says put 30% of your body weight on the cane. Pretty vague, right? I have no idea. Right now, is this 30%? Is it more or less? Have no idea. And they give you a bunch of other things. And none of them really made sense to me. I don't know if I'm using the cane properly or not. So we had a geriatric doctor who came to my class, talked about these issues. Some issues she mentioned, we had no idea what to do about, and some we did. So the student came up with what we call a smart cane. That's an actual picture of a smart cane. So basically what it does, it has a bunch of sensors, it has an embedded computer in it, it has a radio. So depending on how much pressure you put on it, it will tell you by either through your cell phone or by a buzz sound. We have different method of coaching, whether you are putting too much pressure or too little pressure on it. It also has OnStar capability. One of our doctors said his grandma fell behind her house, and for 2 days nobody could find her. She was just lying flat. So this has OnStar capability. If you fall down, after a few minutes, it's going to call 911. So we thought, we showed that in our review that we had in my class. There were some VCs and some business professors, and among all the projects, they thought, oh, this is not a bad idea to do a spin-off. So now there is a company called BioAssist out of these labs, which is building these canes, or is starting to build these canes. So imagine, the students not only get this idea, not only they can explain it to somebody, and there are many challenges. There are compiler challenges, there are protocol challenges, all sorts of things. So, but of course, the students who work on this, they kind of got to learn all aspects of it. There got to be mobile device challenges, the kind of software you run on your mobile PC and all that. So visualization, we have built a very sophisticated visualization system. So there are all these issues that hardcore computer science engineering, computational issues. But one prefers to work on one or the other. This is a computer. That I don't know. So very exciting, and students just love this. So this is one example of thing that came out of my lab and out of these courses. There were many other things, interesting, challenging, but it didn't get anywhere. Example, a knee hammer you have all seen. The students came up with an electronic knee hammer. It measures everything. It has accelerometers and all that. We showed that again to various business folks. They said, absolutely a horrible idea. So we killed that project. But still, they learned a lot in doing it. Child obesity, you all have heard about it, right? The issues involved. I see that every day, right? Kids are in front of their video game all the time. Typically, 30% of children are overweight and 15% obese. The trend is upward, not downward, unfortunately. Children spend about 44 hours a week in front of a screen, whether it's their handheld DS system or the Wii, which is probably the best of them all anyway. just typical computer games. So what do we do about this? Again, we had a doctor in public health who came and talked about this. In fact, this was his slide. So we gave this to the class, and they came up with a really neat idea. The idea was this. They took the existing, if you're familiar with that Nike iPod system, they give it to a kid. So it's a very little sensor. You can put in kids' shoes, pockets, what have you. They come home, and automatically, with no parent supervision, they're going to get TV time or video game time, depending on how much activity they had that day. So this sensor measures how much they've been walking or running or what have you. They come home. If they've been sitting all day, they get 1 minute or 0 minute of TV time. If they've been running around all day, they get half an hour. So all automatic, right? Parents probably don't have time.
Joe never understood why he could rent my shoes for 25 cents a day.
Exactly. So this started with a child obesity because that's where the problem is. Now we have an adult, an elderly version of it. And for adults, we added a social networking aspect. Because if I see that you are exercising every day, I'm going to get jealous. I go and start running. I don't want you as my friend to see that I haven't done anything. So these are kind of things that develop. So this is what students see as immediate application. Of course, there are technical challenges, but they see this application. They see the marketplace, and they just love this. UCLA see the challenge. That's why they are funding us. Industry sees a challenge, and that's why they are funding us. So it's really win-win situation for everybody, and we love that. So kind of more numbers on children and obesity as yet another project. By the way, this project was turned into, so we talked to two groups at UCLA, and they want to do a massive deployment of this project. Let me tell you what they are. I just mentioned it to Jan today. One is the so-called 70 block project at UCLA. So 70 block is an area in South Central Los Angeles, a relatively poor area. We are working with public health to provide a similar technology to high school students so they can wear this. And we want to quantify that their activity as a result of this and coaching and all that has gone up. And if we can establish that, then there is already establishment of activity related to other diseases, diabetes and all that. So that is already established. So in South Central LA, there are 10,000 people who would be user of this. And in UCLA HealthNet, which is an insurance type company, there are 12,000 users. So this little project started in the lab is going to be deployed, or at least we are planning on it, in collaboration with industry at a very large scale. And the students will be in the center of this. So they are very excited. The other project that we have is a personal UV monitoring. In Southern California, that's a major issue. 1 out of 3 adults get some sort of a skin cancer in Southern California. 1 person dies every hour because of skin cancer-related issues. Oh, this is California, Southern California, not California. Sorry, ugly pictures, but facts. These are what you get. Melanoma and other related issues. So what can I do about that? Typically, I have friends, very young friends, who have had a skin cancer. What the doctor will tell them is, of course, all sorts of put this on, put this cream on and all that. But more than that, they say stay inside, avoid sun at all possible expenses. So what we did in this project, we came up with a personalized UV monitor. There are a large number of UV monitoring websites, but they are very generic. You just go there and say UV index in Los Angeles is 7. What about my area? Is it the same way if I'm skiing or if I'm at the beach? The numbers are very different. So we came up with a little Band-Aid that we call a smart Band-Aid, wireless. People put it on their face, their hand, their hat, wherever. And it will monitor their personalized UV exposure time. Exactly. So very accurate, and it's only for, so if you've been home most of the time, maybe you can actually go to the beach for an hour. And so you don't need to stay home all the time. And this is going to give you that feedback. Plus this personalized information is we programmed Google Maps. It's actually going to feed Google Maps. It becomes a social networking site where you can see, based on these personalized information, what the UV level is at localized area in your neighborhood. So you can help this and vice versa. So it's an environmental monitoring project which could work well with the Microsoft, for example, environmental project that they have ongoing. So this is another one of the projects that many folks who heard it thought it's a very good idea. So wireless health is really, at UCLA, is really all about individualized medicine. You go to a doctor once a month if you have an issue. That's not enough to monitor you. If you have foot ulcer, and I showed you all about the amputation, going there whenever you have already the ulcer, that's too late. You need to have this continuous monitoring. So a few other projects. There is a project that people did. You look into the camera. It kind of, I think you were there actually for that project. These are actual working prototype. It monitors the movement in the eye. They did this for, so we got a news from one of the doctors who came to my class. I was shocked by this. Many bus school drivers come to children's bus school drivers, 7 years, 8 years old. They come to work drunk. So, and I don't have the exact number, but it's not small. So they came up with this project so they can look at people's eye movement and based on that, statistically at least say if a bus driver is drunk or not. So, you know, potentially useful application. And it could have many other applications too. One of the students, when you were there, he said he wanted to use that in playing poker. Apparently based on movement of the eye, you can tell if somebody's bluffing or not. So we told them, don't mention that, please, because we have to worry about ethical issues too. Yeah, I suppose Greek, the whatever in Vegas would fund this. I don't know. Absolutely right. So, you know, some of the cars have these breaths, so you can add the eye and make that into a complete system. Yeah, very good. Plus, the other thing they like for the police is you can actually measure this, record this, and save this on your cell phone. So when they go to the court, they have actual data to show.
Interestingly, that checking the eye will also uncover drug users. Police in Denmark have been trained to look at eye movements.
Absolutely. Right. And the other thing we have heard is because of medicine, that kind of drug overdose, you get imbalance. The cost of imbalance in the US is huge. Last year was $20 billion. And effective October 1st, 2 months ago, if you fall in the hospital or any kind of thing that you did not have when you went to the hospital, the insurance will not pay for that. So if you can detect these imbalances because of whatever, somebody being laying down for too long on their bed, you can actually make this detection and prevent that. So the market is huge. Of course, you know, the industry to come after these technologies is going to come slowly, one by one. The only successful thing we have seen recently, we were talking about that, is the Nike iPod system. So the market is there. People are ready for this technology. It just takes time. It really reminds me of mid-70s when the CAD industry was developing. That's what I was working on. It was at a very similar stage.
A lot of heartbeat systems out there. So one simple.
Absolutely. So CardioNet. Yeah. So CardioNet, who did heart monitoring of San Diego, they just went public and they did great. So that's the example we use for our startup justification. Absolutely. So everyone is ready. Plus, some of the traditional industries, Intel type, are looking for new business opportunities. They can't sell, faster chips anymore. Maybe you can comment about what, the new areas that Microsoft is going on. But we are hearing Qualcomm is one of our partners. We are hearing for industry looking for new opportunities. And $2.5 trillion is a lot of money. So yes, this was one of the earlier projects, very similar to Wii idea. The idea is to have a computer game, in this case playing ping pong, but actually people would interact with the board, so it makes kids to actually move. It's not purely moving their hand with video game. It's having some physical activity. So the idea that Wii has. This was another project that people did to help the colorblind. So they take a color movie and they change the colors to make it more visible to colorblinds. I haven't really researched this problem myself too much, but when they presented the idea, we thought this was a really bad idea, because we thought in order to make something more appealing for colorblind, you just do a simple switch. Green goes, if you're green colorblind, you just make green blue or whatever. It's not that simple. You got to look at the neighborhood, so there is some serious image processing going on. So that was another project that people did. You see in a lot of things, they got to talk about how many people have this issue. Is this a real problem? How much would you sell your... So we make the students to kind of think about this. They are not business experts or anything, but it kind of forced them to think beyond classroom.
It's amazing. When I was there, I seen how the knowledge base has been built up. When students do research, they have to come up with the ideas themselves. So they get statistic data and they get all these different fields. That's very impressive to me. And they're having fun with that.
They have fun. Because they could show any of these to somebody and they get it. Anybody out of computer science. Yeah, this is another. So we use these iRobots, robots that you probably have seen to play chess, all automatically move and all that. So those who have interest in robotics, they do that. There is a mini golf project, etc. So 70% of the projects are related to wireless health, but we don't limit that. So things I've learned is students love it. We love it because it's very exciting for us. It's a new area, whether it's from a funding point of view, from getting attention of our deans and university. Last week there was a fundraising at UCLA, which is called Rediscover UCLA. They have this once a year, and people who come and attend are people who have been giving to UCLA typically $1 million a year for the past 10 years or so. So kind of rich people. And they asked us to go and present this idea. So getting this kind of attention for us as faculty is just really exciting. And we see this all over. The other issue that we always had in computer science is having female student minorities. We've been encouraged to increase that. There are many programs going in that direction. So that now is the least of my problem. Let me show you my lab. I basically pick, so that's me, by the way, first one. Postdoc student, graduate PhD student, lot of females, minorities. So don't have any issue with recruiting. A student come and take one of these classes and they all want to join. So we kind of decide who is going to join based on, of course, their intellectual ability, hard work, and all that. So it's kind of neat, very good experience. Very challenging. For 4 years it was, or 3 years, it was frustrating, but we really believed in it. In this case, having UCLA Hospital next to engineering building, that kind of helped. We had an internal workshop last year where we invited 20 medical faculty from UCLA to come, and 50 of them showed up. So we are just overwhelmed. So we don't have much resistance in kind of going forward. Took a lot of time, but I think it's worth every minute of it. Any questions, I'll be happy to respond to.
To become nerds and program all the time, they don't have to worry about it.
Good points. Side benefit, please. I'll pass it to her, and absolutely.
So these are people, so they come into this with what background?
Computer science, electrical engineering, biomedical engineering, mostly. We have math. We have a statistic, but they, of course, had some introductory computer courses.
So this is an example where we take people with computational or math skills and we get them involved in scientific applications as opposed to the other way around, which is most of what we hear, usually what we hear about.
Right,
okay.
Absolutely.
We got to go.
I agree.
It's such a successful example. Looking at from computer science perspective, people are trying to solve their increasing movement problems, and they're kind of trying to promote gender equity. This one is just somehow naturally solved. I see those girls, they just identify themselves so much with the healthcare. They wanted to come up with tools and devices to help people, and they can bring it home and talk to their grandparents. So it just somehow appeals to the female students as well. I saw that in your lab. It just,
Yeah.
So several socially related problems somehow just got resolved.
Yeah. It reminds me of the book An Accidental Empire. I don't know if you have read that. That's about how Silicon Valley was built. It's not like a visionary sat down and said, let's build Silicon Valley. All these things kind of came along by accident. Of course, we are very pleased, but it wasn't honestly our vision that once we make this happen, all of these good things will happen. Purely an accident.
To answer.
Silicon Valley? Eventually. So, a lot of people went to Intel, and a lot of them. A good example is the Communication Valley, Orange County. Broadcom and all that, all university projects. Henry Samueli, who started Broadcom, our colleague at UCLA. But
A strong education base will always
help. Yeah, you need to be at the right time, at the right place, and all that. I agree with that.
You did have difficult time in the beginning, the same kind of thing that you mentioned.
Yeah.
Interdisciplinary boundary problems, departmental.
The first thing that the doctors taught, some of them, when we talked to them, they thought we are technicians, basically. So they said, can you write this program for us? I said, that's not why we are here today. But thank you.
The lead center at the University of Wisconsin has done studies on computing and minorities, and they found very conclusively that if it involves application, if it involves problem solving, particularly real world problems, then women are much more attracted to it than they are to hardware and software.
Yeah.
So that's true for all of the computational science approach.
So, could you elaborate a little bit on, you said the first 3 years were tough, and now it's all a success. So what were the hard things you had to break through besides what we already mentioned, the boundaries?
So definitely having a common language and vocabulary with the doctors. And many of them are not willing to do that. They are busy with their practice and all that. So it just took time to find the right doctors, sometimes educating them, and vice versa, them educating us. One of the mission of our institute is end-to-end system. We don't build gadget. We build a system that starts from a disease, goes all the way to guidance and all that. So that was very important. We didn't know that at the beginning. We came up with this gadget and we say, what can you use this? They didn't understand it. They didn't care. So educating each other took a long time. And kind of a promotion. So now on campus and off campus, they hear this buzz a lot. They have seen some success stories. So now they are getting it. So this thing wasn't ready. Even if all the doctors were really willing to adopt, the technology and the mentality and the economy wasn't ready 5 years ago. Today they are. But it's a lot of hard work. So non-tenure faculty, this is absolutely a mistake for them to do anything similar to this, my opinion. And that's what I tell them. They need to focus on their tenure, really.
And you briefly mentioned, because I have a feeling that also just the technological development just the past 5 years has meant it's much easier to actually produce results, because now you can buy cheap sensors, you can buy cell phones cost essentially nothing.
Right.
And a computational base in a cell phone, well, it's just there and it can be used, and there are development tools and so on, and that makes a big difference too. So I'm also wondering what percentage of the success is that you now actually get the tools and the equipment and so on.
So that's a big part of it. So there are, for example, some of the shoes we have built for diabetes, ulcer. If you look at it, you think it's a normal shoe. Why? The radios are so small, we just embed them in the shoe, the sensors, the embedded system and all that. So that's a big part of it, technology. All the cell phones that is available and the power they have, and they have open system. A great example of some of the Windows-based system and Android-based system, totally open system, just like a computer, right? So big part of it. So again, I say being at the right time, at the right place, that's a big part of it. And then you hear all these news that more and more that there is something seriously wrong with our healthcare system. You see the buzz all the time. They say the meltdown of the healthcare system, when it occurs, it's going to be so big that today's meltdown is minor compared to that. So everyone is kind of panicking. Government, universities, insurance companies. So it's really a lot of dynamics kind of coming together.
And I will end up by giving you a little idea that I saw recently in a camera. It could be operated by tapping it. It had an accelerometer in it, and using that as an input device for people who, don't have much mobility or have had a stroke to actually operate stuff that way.
Excellent idea.
And actually, I gave this camera to my son, and I didn't know that it had this functionality, and that's just what he needs, because he's going to be a ski bum for 4 months all winter. And then you don't have to take your gloves off to operate the camera.
Just tap it.
Just tap it.
Excellent.
Okay, thank you very much.
In the courses? So we had it for 3 years. The first course is required from everybody in our department. My guess, a few hundred, but I can't give you the exact. Yeah. And you kind of asked that question, what kind of job they get. These are really in high demand, both faculty-wise. So I have one of my students, Tammy. So she's going for a faculty position now. She has a very unique set of skills, and people just love to interview her. For example, our department is looking for faculties of this type who are really multidisciplinary. We are not looking for compiler folks. We are not looking for OS, for theoretical computer science. The chance of getting them hired at UCLA, maybe over the next 3 years, 5 years, is close to zero. But folks like this, computational biology maybe, they just seem attractive. We like them. The deans love them. The admins love them, etc.
Yeah, so it's very interesting, because the UK Engineering and Physical Sciences Research Council have just announced 44 new centres for doctoral training, which are in some ways or another computational or interdisciplinary based, in everything from the built environment through biology through music, I think one of them. So it is very good to hear that this sort of centre that does seem or program does work very well.
Right.
So
very good.
Okay, we'll move on now. Let's just give him Majid a hand. It's a tiny laptop you got there.
Let me just move it a little bit over in case you end up talking to your left. There you go.
See, when I see that in these courses, another thing is that you gotta recruit the best students. From level to level, undergraduate to graduate, and then in turn, these graduate students do the BA. Similar to what I did at PA.
Oh, goodness, it should be. And then, it's just good
When they become so demanding.
at sort of kick it here. And detect display. This is there. Okay.
Good.
I just needed to take some action. There you go. Okay. I know how to do that.
Excellent. Good. Okay. So I'm Charlie Whitaker. I'm from the Koch Institute, and what I'll tell you about today is a little educational initiative we're beginning called Turning Biologists into Bioinformaticists, a practical approach. A little word about the Koch Institute. It's a multidisciplinary operation, MIT molecular geneticists, cell biologists, and engineers. It was originally the Center for Cancer Research. It's joined forces with a bunch of engineering faculty. So there's 24 faculty from the biology department, engineering department, 170 PhD level scientists, 175 graduate students, 70 undergrads, and 70 technical staff, so a large number of people in the research force. Within the Koch Institute, there's something called the Swanson Biotechnology Center that supports their research. And what that is 15 core facilities covering services from glassware all the way to flow cytometry, transgenic animals, that type of stuff. And one of the facilities is bioinformatics and computing, and that's where I come from. Our role is to assist Koch Institute researchers with their bioinformatics needs, and we do this primarily by collaboration. We work hands do the work for them or closely with them. But the other thing that we do is we try to train them. Really, the only problem that we have is that there's only 3 of us, and the third one just joined beginning of October, thanks in large part to Microsoft's support. Is we just can't keep up with the amount of work that we have. So we have to raise the overall level of computing skills in our researchers to the point where we can handle things. What's happening with biology, like everything else, is that it's becoming more and more a computationally oriented field. And the things that have driven this transition had to do with genomics. Obviously, the sequencing a whole bunch of different genomes has made it possible to do genome-wide annotation analyses. Microarray platforms are commonplace now for all different kinds of applications. And then in the last year or so, we've seen much more prominent use of these massively parallel applications like next-generation sequencing. That I'll mention that a little bit later. But there's other kinds of things here, high-throughput compound screening and automated image analysis and that type of thing, all of these computationally intensive. And our biologists are definitely underprepared to handle the demands that this type of work puts on them. In fact, if you have conversations with them, some of them they are biologists because they've sort of avoided math and computation throughout their careers. So that's the kind of people that we're starting off with. One of the things at the beginning of this program I wanted to do was to do some sort of a survey to get an idea of what people think and also sort of assess their skills. And so I designed a little survey where I went to their space and talked to them and gave them some tasks to do. Some of the things I learned from the conversations that happened was there was intimidation.
with working with a command line. I mean, everything that they do, they're familiar with sending email and making presentations and doing some Excel stuff, but they never interact with their computers by typing commands at a command line. And one person freaks out when he sees the blinking cursor. Another thing that I saw is a general lack of awareness. And some people thought that they knew all they needed to know, that they didn't know. I was showing one guy some Unix commands that probably could have helped him out, but he just was frustrated and said, I have a Mac, I don't need to know this business. And then dependency. I talked to another guy that said I was about this, and he said, well, I have a Grace. And what a Grace is a really talented computational biology grad student that shares a bay with him. So he's lucky to have a Grace. Everybody has bioinformatics core facility, but we're a little too stressed to help everybody. So this dependency has to be overcome too. So the computing skills that I gave him, I gave him 4 very simple tasks that could be all done with a single line Unix command, also handled very easily in Excel. I just wanted to see how they handled things, and then graded them A, B, or C, A being unable to do it, B completed the task but had to go through some kind of complex effort to get there, and C just did it very simple. And these are the results. The file management task, people either had no idea how to do it or could manage it. Both the text summary and the numerical analysis tasks were really easily done with Excel, and a lot of people tried to do it with Excel with varying degrees of success. People seem to associate Excel with numbers more than with text. There were some people that handled the number thing easily but didn't think to use Excel to summarize the text data. And then a text manipulation problem where most of the people had some idea of what they were supposed to do but didn't really know how to execute it. And one of the things that was nice about doing this survey by going around to their desks and their benches was I had a chance to look around and see what was there. And 3 out of the 10 of the people that did this with me had some kind of computer book at their desk, like Bioinformatics for Dummies or something like that. But I think what's clear from the results is that they're, generally speaking, not really using the books very much. So that method of education isn't working for them. What was a real common response or comment was that they would learn something new about how to do things with computers, and if they didn't use it again immediately, they'd forget it and lose track of it. So they all wanted some kind of a reference resource that they had available. And then there was this command line frustration that I found that people just almost refused to interact with their computers from the command line. And then this attitude that 3 out of 10 of them had that they just knew all that they needed to know already, so they weren't going to invest any more effort. So I think this is a sort of problem that we have. And back in July at the Faculty Summit, Mark Guzdial gave a talk about his experience teaching computer science to all Georgia Tech students. So that's the kind of transition he has to make. And it was a really good talk. It's available online if you want to take a look at it. And I got 2 really important points from it. One, he made a great case that computing should be taught to everyone. So those people, those 3 out of 10 that don't feel like they need any more computing education should probably see his talk. The other thing is that probably the most important thing about teaching this stuff to people is that they need to see a context. If they see a reason for doing something, it leads to them spending time on the job and really effectively learning it. So I think we have a much kind of a different set of things we need to teach our biologists. It's maybe a lower level education covering a little bit broader set of things that they need to do, but it's the same sort of transition, and I think context is essential. I was thinking about that idea of context, and one thing that I remembered back to was what happened with PowerPoint in the biology department. So when I was a postdoc, I first started as a postdoc, nobody used PowerPoint. Everybody was still using the old slides. And then as soon as a few presentations started showing up, everybody and their brother had PowerPoint. It went from absent to ubiquitous in a really short period of time. And the other thing that happened, you could almost always tell somebody was giving their first PowerPoint presentation because they would put as many different animations into the talk as they could. And I think but these 2 things are telling, because these useful tools, if they see a use for it, they're going to jump right on it and use it effectively. And they're also going to drill down and find, really learn it, all the little details about it, not just what they need to know. I think it can be, maybe. Exploration could lead to creativity, So PowerPoint was a kind of an example of a very contextually relevant computing thing that was taken over by biologists really easily. And I think maybe another contextually relevant thing that's going to drive a big jump in computing is this next generation sequencing that I mentioned. One of the vendors, the machine that we use in our center, is made by Illumina. How this works is that you take a relatively large number of images. I know I've seen some data sets described today that make these look small, but for us biologists, this is a huge data set. You run it through some image processing and analysis, and out the other end, for each one of your experimental samples, you get this giant text file with millions and millions and millions of rows of nucleotide sequence. One kind of illustration of how much data is produced is we have just one of these machines. It's been in our institute for a year, and about half of its capacity, we've resequenced the mouse genome more than 3 times. So just with one machine in half capacity. So it's all over the place. And the other thing about it is the data can be applied to all different kinds of biological problems. So it's not someone that's just doing gene expression analysis that needs this. Pretty much the applications are limited only by a person's creativity. So more and more, I think next generation sequencing is going to be the workhorse of a biology lab. With files this size and data sets this size, typical point and click kind of tools that biologists are comfortable with using like Excel just can't handle the data. It's not going to work. But very simple routine command line tools like basic Unix utilities or Perl scripts, relational databases, R, they're just designed for this. They handle this data very effectively. So what we're thinking about doing is creating these little nuggets of information for people that have a high degree of contextual relevance, instruct them on some computing thing, topic, and then have the people be able to go back and refer to those nuggets so they don't need to relearn syntax to reuse the tool down the road. And of course, the idea that this will lead them to self-learning and instruction on their own is what we're hoping for. There's some evidence that this is true because an example just during this little survey that I did, I showed the guy that made the comment about having a grace, a little command using awk to summarize the data set. And he had a big giant next generation sequencing data set in his hand. And about a week later, he wrote me an email with a much more complex awk command in it that he'd used to investigate his data. So for this guy, he clearly saw the utility of the tool and went and ran with it and very quickly learned a bunch of new concepts. So I'm hoping that kind of paradigm continues. So what's the best way to present these things to people? At the end of January, coming up here, we're going to have 3 2-hour sessions in a formal classroom, about 20 people in each session. The room will hold about 20 people, where we'll teach an array of these things covering a variety of different topics from Excel to microarray data processing. We also have the opportunity to run small group sessions with these things and show a smaller number of people, a smaller number of things in a less formal way. I think it's also important to train people while we're collaborating with them, to not just do things for them, but try to show them what we're trying to, what's going on. Another very effective thing, I think, is the idea of these walkabouts. When I first started in the facility, a person that was running another one in town told me some of the best ways she gets interaction with people is to go out into the labs and wander around, and people will grab her in the hallway and talk to her. And I think if we just approach people as they're sitting at their computers and doing things, we could show them a thing or two, and we'll immediately have a great sense of what's contextually relevant to them at that moment. And then obviously the material that we generate will be available online, the lessons, and also possibly video tutorials. I think there's a few challenges that we face that we don't really know what the best way to get at people is, so we'll be paying close attention to that. Another thing is if you generate a large number of these little bits of information, how do you organize them in a way that people can find their way, find what they're looking for? Some sort of a hierarchy is certainly a first step, but I'm also interested in maybe some kind of a wizard where people can describe their problem and go through a flowchart type thing and get at the tool that they need. I'm also interested in some sort of a wiki where we can get information back from people and see what they have to say about things and what they need to know. And then as far as monitoring our training progress, this is something I'm also interested in. And one of the things one of the obvious ways that we can monitor the thing is if we suddenly have no clients and everybody's a bioinformaticist and we're out of business, we will have done a great job with the training program. But probably won't happen. No. So that's the story of our bioinformatic training progress right there.
Thank you very much. Questions? Will the modules be in context of a project?
Yeah, I hope so. Yeah.
Because I think a lot of these students probably went into biology because they didn't want to have to do math and computing.
Yeah. Yeah, so the idea would be, they will give them some task that they're going to encounter handling these data or a very standard thing. These folks are really busy with their own field. There's a lot for them to know in the biology field. They don't really have time to invest, so they really need immediate returns on these things, or they lose interest very, very quickly.
So you said that some of your biologists were anti the command line.
Yes.
I think it's a usability problem where we as either computer scientists or computational scientists try and impose working patterns on our users rather than sort of work out where we should be maybe working harder to develop our tools so that it fits in or can fit in with the way that they do things already.
Yeah.
Because that's one thing that we've certainly found. If we can introduce the tools in such a way that almost the users don't see it, then through either standard access, adding to workflows and things like that they're already using, that's the most successful in the longer term.
It's a good point.
It's a matter of the knowledge base. So with Microsoft Office, PowerPoint, we have this common general knowledge now online, so we can provide those kind of applications. Whereas something for scientific research, we just have to put ourselves more into the environment with the scientists so that we can come to understand better what exactly would be another killer application for them.
Yeah.
Strange to say workflows is something that we find very hard. And it seems the most natural thing for computer science. It's sort of a very obvious generalization from the flow chart, which is one thing people understand in our background about computation. And yet, when I talk about people at the academic computing center, they say don't do it because people, except for the very, very simplest workflows, don't understand what to do. It's very strange.
Yeah, I just want to make a comment and also probably add one more thing to your challenge, because I happen to also do the bioinformatics. So in terms of strategy, what are the ideal training strategies? I don't have ideal strategy. I just have one strategy for your reference. One issue I observed that those scientists who are working on the informatics, in reality, if you want to really help them get enough background so they can handle all those themselves, that takes long time because they basically it's completely different right brain, left brain kind of training. So what I tried at Georgia Tech is I was trying to team them up. Basically team a computer science background with a biologist and then give a topic while I'm doing the training. So they have to go through the whole process together in the process. That seemed to work well compared to initially I just assigned them to the group that's totally biologist. Just one strategy, not whether it's ideal or not, I'm not sure. However, I have another challenge that's related to what you're saying, what's the optimal way to achieve the nuggets and how can we monitor our training process. One of the problems is informatics field is it's not static. It keeps growing. It keeps changing. We have to keep giving updates. So to me, another challenge I have been into, because I have been training my people mainly in CA Big related informatics, is all the tools keep changing. So the maintenance, all those updates completely mess up some of the training measurement process. So in that regard, I would love to join hand if you're interested, so we can see what might be a way.
Yeah.
Because that's one of the problems I observe in this computational world, which is everything keeps changing, right? After you understand C, now there's C++. After you finally got understand C++, now there's Java. Now there's Perl. Now there's Python. All these other things that keep changing. Now it's J++, all those things. So how do we keep up with that? Even as the people who are trained in this area, we have problems, not to say all those other students. That kind of issue is something I would add to your challenge list.
Yeah, for sure.
Well, it looked like you were suggesting we just stick with awk, which is how many years old?
Hey, it's effective.
More questions?
So more one actually almost for the audience as much as the speaker. So of the people here, how many people wrote their thesis or still write papers using LaTeX? See, now a very interesting thing is, so my wife very recently completed her PhD in pharmacy, and her thesis was made up of 11 Word files, 9 PowerPoint files, 3 Excel spreadsheets, and so one of the tools, and the problem was actually how you fitted it together. She thought nothing of, and none of them were numbered at the bottom because all the numbering was done manually when you printed it. And her and her group thought nothing of doing this, and I spent many an hour trying to convince her that this was really not the way you want to go writing a thesis. So I think the thing from this, though, is we need to make sure that we ourselves are teaching people the appropriate tools for the appropriate scenario, because neither LaTeX, which is completely, utterly unsuitable for a bio-experimentalist, or using Word to write your thesis are the appropriate tools. What we actually need to do is look out there for those to make sure that we know, so that we can advise people where appropriate as well.
Okay, and let's give Charlie a final hand. We're almost out of time, but I'll end. I'll ask a question now. How many people here, if we had a similar type of session, would show up next year for a similar type of session? So that's almost everyone. It sounds like we should have one next year.
Yes, that we will.
Would it be possible as well to, in some way, either make it connected through video conference or something else? Because there's a lot of people that are doing this. For example, the doctoral training centres that are taking, here in Oxford, are taking engineering and physical scientists and turning them into computationally aware life scientists. But those people won't come along to something like this because they don't have the time.
Live
It
casting.
seems to be here, but
Yeah,
there are a lot of people that are doing this whose input and have been very successfully doing it. So, for example, the doctoral training centres in its 5th year, and so they are obviously doing something very, very well or very successful because they also managed to get refunded. And so, I think we're making sure that we can get the input from those people that are doing that here, because they won't come along to an eScience.
Now, if it's just for 2 hours, it's not maybe not worth the trip from your, or get the funding for it either.
So, question, since there's a number of, there's a lot of these programs going on around, what are we doing to, courses are being developed, modules, labs, and what are we doing to share those in a sort of way?
That's us. I mean, Microsoft is a facilitator, so we want to provide
also a education program at the Supercomputer Conferences, and that's really a week long, just to train.
No, I know that, but I'm wondering, are you guys encouraging the leaders of these programs that you make this available when you develop the courses? Because if you go to a publisher, it takes 5 years to put the material.
Exactly.
How do we, and we don't necessarily write full text, we can leverage each other's content and what we're developing for these courses much more effectively if we somehow put it in out there.
There's also workshops at professional conferences.
Right.
So when we publish this takes only like 2 months, we can put it in print. And the next step is
Yeah,
put
but
it in the journals.
I guess I'm
Course material and all sorts of other stuff. Yeah.
encourage is
Yes.
online electronic license for people to use it more, so it's agile, dynamic, and all of that. So, there's online repositories, and print is sort of in the past. Yes, you may want to print it, but it's not the first thing you should put it.
No.
David?
Yeah, well, so first of all, I think an awful lot of course materials are available, so it's more a case of actually publicising their location.
Right.
And secondly, making sure that it's available in a nice open format or a nice sort of uniformly accessible format like PDF or something like that, where those that aren't using specific tools are able to, for example. I think it's
Yes.
important thing to make sure that as well, it's going to be something that's going to live on. Because, so the amount of trouble that people have these days when they're sent PPTX and docx files is just
No.
So, Jan, do you have any statistics on how many programs and courses are out there? I mean, out in the universities around in the U.S. and around the world.
No, I don't.
No, but that would be a good idea to know. I've been starting to dig into that.
You need to, well, the CPAP program is going to do something like that. We need to cross-link a lot, because there's your effort, there's the NSF effort,
Yeah.
There's a whole. I actually would suggest almost that the funding
CPAP is revitalizing undergraduate
Yeah,
education.
it's not specifically about eScience, but you can definitely.
We know that it has a high degree of overlap. And so,
Yeah.
what would be useful, I took on the section for that, for the eScience. What would be useful is your website to cross-link some of these things, so that this community here has easy
Right.
access to it.
Right.
And we need to talk to
We definitely should.
Yes.
Yeah, Microsoft
And-
has this academic alliance repository, but so far we're lacking on Microsoft technology-based computer science courses. So I can give you exact numbers. In this area, it's new. I think we talked about it before. The reason that I didn't start to collect the curriculum in this area is because we don't know how to classify them in order for people to search easily. It's not in our existing taxonomy.
So the eScience section of MSR is not taking sponsorship of this?
We're not integrating yet. So if we wanted to, and this is something we can talk about. Yeah, definitely. So they don't go to the academic alliance repository like I was saying, because we don't know how to tag it appropriately.
Okay.
It's not,
Da-
right now it's ACM knowledge-based tag.
Dave?
So if people were to mark up with keywords their individual course material, then Jeremy Frey, for example, showed a really great tool for linking together
Right.
using keywords. A lot of stuff that he was using on his science blog stuff, blogging on that. And so those sort of tools are available, so people can, I could search for those sort of courses for computational biology, for example, the specific ones for data mining.
Yeah.
And that would just be a case, for example, of using the Azure Cloud to host a front end so that you can actually use that tool.
Ruben?
It's kind of silly, but there's a group of people doing exactly this right now at the other conference. So Bob Hamill, Scott Lathrop.
You mean the eScience IEEE?
Yes, and they run the computational science pathway to the National Science Digital Library, which is also a natural place to put this and to overlap. So.
This is the first time that we joined the physically, I guess, location-wise, we're joining the hosting. But I guess content-wise, we should.
As well.
Right.
Yeah. I think everyone would like to.
Right.
So, I would also suggest that if anyone else has, good ideas and so on, that you mail me and I'll collect it with Jan. Okay, and then I'd like to thank you all for coming.
Thanks, everyone.
Thank you.